Okay, so now we've done a couple of examples where they gave us a value of the random variable and asked us to find a related probability or proportion. But sometimes they'll give us the probability or proportion or percentile and ask us to work backwards to find the value of the random variable, and that's what I'm about to show you now. For example, we might want to know the height of a 3-year-old girl who's at the 20th percentile. Or we might want to know the cutoff scores for the middle 90% of scores on a standardized test. So here's how we go about finding a z-score that's associated with a known area. What you're going to do is look at the area part of the z-table. Locate the area, or if the exact area you want is not there, find the closest value you can. Then trace back to the edges of the table to find the associated z-score with that area to its left. Remember, all the areas in the table are to the left of the z-score that they're matched with. If you need an area to be to the right, you can do the same thing, but just remember when you find the z-score, it will be the wrong sign and you need to change the sign. So let's practice a little bit together. This says find the z-score such that the area under the standard normal curve to its left is 0.35. A picture always helps, so draw yourself a standard normal curve. Now if the area to the left is 0.35, we know that the z-score must be somewhere over here, because if it were here in the center, the area to the left would be 0.5, which is too big. So that z-score must be over here somewhere. Draw yourself a line to represent the z-score. Now because it's on the left side of the curve, you know it's going to be a negative z-score. And now shade the area that you're thinking about and go ahead and label it. The area is 0.35. You need to be very careful to keep a clear distinction between area and z-score, because what happens is people get confused about what this number represents and they come over here and try to treat it like a z-score. This is an area, and we're trying to find the z-score that matches an area of 0.35. So now come over here to the table. Remember, the table is arranged so that the areas are in the middle and the z-scores are along the edges. So since the area we have is 0.35, we need to look here in the table for an area of 0.35 or as close as we can get. So I'm looking here, I see that I have 0.3594, 0.3557, 0.3520, and then it drops down to 0.3483. So we know that the area we have, 0.35, is in between these two areas that we see listed in the table. And you have to do a little quick subtraction in your head. If you subtract 0.35 from this number, you see that this one is 20 10,000ths too big. And if you subtract this number from 0.35, you'll see that this one is 17 10,000ths too small. So this one is just slightly closer than that one. And so now I'm going to trace this one back to the edges to get its z-score. So the first two digits are negative 0.3. and the last digit is 9. So the z-score we're after is negative 0.39. Now let's try it again. Find the z-score such that the area under the standard normal curve to the right is 0.2. So draw your standard normal curve. The area to the right is 0.2. So if I want to mark off the 20% of the area that's on the right, my z-score is going to be somewhere to the right of center, because remember, if I drew the z-score right here in the exact center, the area to the right would be 0.5. So my z-score is somewhere to the right of that, and so the area that I have, the 0.20, is right here. And now let's go to the table and see if we can find an area of 0.2. It may not be here exactly, but we can get close. So I'm looking down here toward the bottom. I see that I have 0.2061, which is really close, 0.2033, 0.2005, that's very, very close. Let's look at the next one. The next one is 0.1977. Okay, if you do a little quick subtraction, this one is 23 10,000ths too small, and this one is only 5 10,000ths too big. So this one is the winner. And the z-score that goes with this area is negative 0.84. But remember, the way we drew our graph, you can see that the z-score has to be positive. And in fact, the area that we shaded is to the right. So we know that the table is going to tell us the wrong sign. So this is actually not negative 0.84. This z-score is actually positive 0.84. You see how the diagram helps you? When you look at the diagram, you can't possibly believe this is a negative z-score. So you need to learn to draw the diagram correctly, and then the diagram will help you get to the right answer. Here's another one. This one says find the z-scores that separate the middle 99% of the distribution from the area in the tails of the standard normal distribution. So we start with a sketch. This time I need two z-scores, and I know that the area between the z-scores is 99%. Now if the area in the center is 0.99, then the complement of that is what's in the tails. See, the only thing that's unshaded is what's in the tails. So 1 minus 0.99 is 0.01. That's the area in both tails together. So the area in each tail, since there are two, is 0.01 divided by 2. So the area in each tail is 0.005. That's the area that I want to find the z-score for. Now remember, the table is symmetric. So if I just find the z-score for an area of 0.005, that'll be a negative z-score, but I know that because this area on the right end is the same, this z-score is the same number, just positive. So now let's go to the table and look for an area of 0.005. So I'm looking for 0.005. So I'm looking up here. I see 0.0008, 0.0021. That's a lot closer. And oh, here we go. 0.0051. That's only 1 10,000th too large. But this next number is only 1 10,000th too small. So this is an unusual situation where we have a tie. Remember, we always take the area that's closest to the area we're looking for, but this time we have two numbers that are equally close. So what we'll do is take both of them, find both z-scores, and then take their average. So the z-scores that match these two numbers are negative 2.57 and negative 2.58. So we'll need to find the average of those, or what's exactly in the middle. So let's say that negative 2.57 plus negative 2.58 divided by 2, that's the average of those two numbers. That will give us a z-score of negative 2.575. So this z-score over here is negative 2.575. And then the z-score over here is positive, but it's the same because the area in the tails is the same. So this one is positive 2.575. Now I know that you may be remembering what I have said previously about z-scores always being rounded to 2 decimal places. That is true whenever we are calculating a z-score. But remember, these two z-scores came to us through the table. We were trying to find an area of 0.005, and the two areas we found in the table were both equally far from 0.005, so we had to break the tie by averaging the z-scores. If we round, we'll just end up with this larger z-score, which defeats the purpose. So this is the one exception to the rule about rounding z-scores. Whenever we have had to average two z-scores, we will keep that third decimal place. And again, just for practice, this one says find the z-scores that separate the middle 94% of the distribution from the area in the tails. So start with a standard normal curve. Draw yourself two z-scores. This middle area is 0.94. And if the middle area is 0.94, then the area in the tails is the complement of that, so 0.06. That's both tails together. So the area in one tail is 0.03. and that's the area we want to go look for in the table. So now searching through the table for 0.03, I'm seeing here 0.0314, 0.0307, 0.0301, and the next one is 0.0294. Now this one is only 1/10,000th over the area we're looking for, but this one is 6/10,000ths too small. So I'll go with this one. And the z-score that matches that area is negative 1.88. And so this negative z-score is negative 1.88, and this positive z-score is positive 1.88. And again, these two z-scores are the same number but with opposite signs because these two areas in the tails are the same, and the graph is symmetric about z equals 0 right in the center. Okay, now we're going to talk a little bit about percentiles. And remember from chapter 3, a percentile is a value that is greater than or equal to a certain percent of the data. So therefore, the 95th percentile has an area of 0.95 to its left. And what we want to do now for practice is find the z-score that corresponds to the 95th percentile. So again, sketch yourself a standard normal curve. The z-score that has 95% of the area to its left would have to be way over here on the right side. So let's shade to the left. That area is 0.95, and so I'm going to go to the table and look up an area of 0.95. I'm going to get as close as I can, and here I see 0.9495, and the next one that's a little over is 0.9505. So this one is 5/10,000ths too short, and this one is 5/10,000ths too large, and so again we have a tie. And this is actually kind of unusual, but it does happen. So the two z-scores we are after are 1.64 and 1.65. And all we have to do now is average those two z-scores. And the average z-score is 1.645. And I can tell that this is a positive z-score because it's way on the right side of the curve. And so z equals positive 1.645. And now let's find the z-score that corresponds to the 30th percentile. So again, draw yourself a curve. The 30th percentile is going to have an area of 0.3 to its left. So that z-score is going to have to be somewhere here on the left side, because remember, right in the center would be an area of 0.5. So a z-score that has an area of 0.3 to its left would have to be somewhere over here. And so I'll just draw that, and I'll shade the area to the left and say that that area is 0.3. Now to find the matching z-score, I come to the table. I look for an area of 0.3. Here I see 0.2981 and 0.3015. This is 19/10,000ths too small. This is only 15/10,000ths too large. So we'll go with this area. And the z-score that matches that area is negative 0.52. And so that's it. The z-score we were looking for is negative 0.52. Now I need to show you a new notation. This is a certain way of writing things, but if you don't know how the symbols are being used, it's not obvious to you what's going on. So sometimes you'll see a z-score with a subscript on it. When we see it written like this, we say z sub alpha. So the sub is short for subscript. So z sub alpha, that little Greek letter is the lowercase alpha. And whenever you see it written like this, what they mean is that's the z-score such that the area under the standard normal curve to the right is equal to alpha. So remember, A for area and A for alpha. Alpha always stands for an area. So now this says find each value of z sub alpha. So here I have z sub 0.01. That means find the z-score that has an area to its right of 0.01. And so let's sketch that. If the area to the right is 0.01, that z-score is going to have to be way over here to the right side. The little shaded bit is only the 1% of area that is to the right of that z-score. and so the area to the left is 0.99. You could either look up 0.99, or since you have the 0.01 here, you may as well look up 0.01 and then just remember that the table is going to tell you the wrong sign. So let's go ahead and find 0.01 in the table, or as close as we can. Here I see 0.0099, and here I see 0.0102. Now this is 1 10,000th short, and this is 2 10,000ths over. So we're going to settle on this one that's a little closer to the area we were given, and the z-score that matches that is negative 2.33. But now remember, this z-score has to be positive because you see it's on the right side. And remember that since our shaded area was to the right, the table tells us the wrong sign. So the z-score for z sub 0.01 equals positive 2.33. And let's try it again. For z equals 0.15, we are looking for a z-score that has an area to its right of 0.15. So that little shaded area there is 0.15. Now come to the table over here, and we are looking for an area as close as we can get to 0.15. So here I see 0.1562, 0.1539, and 0.1515, and the next one is 0.1492. So of course this one's a little over and this one's a little under. This smaller one is 8 10,000ths under, but this larger one is 15 10,000ths over. So we're going to settle on this one, and that means the z-score that matches this area is negative 1.04. But again, when we look at our diagram, we can see that this z-score is on the right side of the graph. Therefore, we know it's a positive z-score. So we are going to say that z sub 0.15 is equal to positive 1.04. Now, it's going to happen pretty frequently that they're going to give you a probability or a proportion or a percentile and ask you to find the value of the random variable that matches that. Now, we have a z-score formula that we can plug x into, but what we want now is an x formula that we can plug z into. So what we're going to do is take our old z-score formula and rearrange it so that it's solved for x. This takes just a little minor algebra, and I'm going to do it with you, but once we get it done, you can just use the formula that we get, and the formula that we're going to come up with is on your formula sheet that you'll have with you during the final exam. So don't panic about the algebra, but let's just walk through this together. If we wanted to isolate the x, the first thing we would have to do is multiply both sides of the equation by sigma. That would let the sigmas here cancel out, and that would give me sigma times z equals x minus mu. Now remember, I'm trying to isolate x, so now I'm going to add mu to both sides, and that's going to give me z sigma plus mu equals x. So that's our new formula, x equals z times sigma plus mu. So again, if I have an x value and I want a z-score, I can always use this formula that was solved for z. But if I have a z-score and I want to go back to x, then I want to use the formula in this form. Both forms are on your formula sheet. Now let's get a couple of examples where we will get to practice with this formula. Here is example 3. This says the heights of a pediatrician's 3-year-old female patients are approximately normally distributed. This is the same data we've seen before. The mean is 38.72 and the standard deviation is 3.17. Find the height of the 3-year-old female at the 20th percentile. So we need to draw a standard normal curve, and at the 20th percentile, that means the area to the left of this z-score is 0.20. So I'm going to draw a z-score that's on the left side of the curve, and the area to the left of that z-score will be 0.20. And now I'm after this z-score, so I go to the table, and I'm going to try to get as close as I can to 0.2. So here I see 0.2643, 0.2327, 0.2033. Okay, now I'm in the ballpark. Now if I go up, that's too small, so let me go to the right a little bit. And if I go right, then I see 0.2005, and that's really close. And if I go right again, that's too small. My choice, so my choices are between 0.1977, which is 23 ten-thousandths too small, and 0.2005, which is 5 ten-thousandths too big. So I'll take this one, and the z-score that matches that is negative 0.84. And now what I want to do is turn this z-score back into an x. I need to find the height that matches this z-score. So I'll use that formula, x equals z sigma plus mu. The z is negative 0.84. The sigma is 3.17, and the mu is 38.72. Add that all up, and we find that x is approximately 36.1 inches. So in other words, we can expect that approximately 20% of 3-year-old female patients are this height or less, and that means 80% are more than this height. And example 4. The scores earned on a mathematics portion of the SAT are approximately normally distributed, with mu equals 516 and sigma equals 116. What scores separate the middle 90% of test takers from the bottom and top 5%? Okay, now remember, they'll always tell us that the data is approximately normally distributed, because if they don't tell us that, then we can't use the z-table, and that's the only way we have to work the problem. So they always will tell us that the numbers are approximately normally distributed. And so now we can draw our standard normal curve, and we want to separate the middle 90% from the bottom and top 5%. So that's going to take two z-scores. The middle area is 0.9. Now if the middle area is 0.9, then that means the area in the tails is 0.1. That's the complement. So now if there are two tails and we split the area between them, then 0.1 divided by 2 gives us an area of 0.05 in each tail. And now we need to go to the table and match this area of 0.05 to a z-score. So I'm looking at the areas in the table, and I'm looking for an area equal to 0.05. And I'm finding that I have 0.0505, and the next one that's a little smaller is 0.0495. And they both are 5 ten-thousandths away from the area we want. So the z-scores that match these two areas are negative 1.64 and negative 1.65. So averaging those two, I find that the average is negative 1.645. So this z-score is negative 1.645, and this z-score is positive 1.645. Now we need to transform both of these z-scores back into SAT scores. So we'll use our formula that's solved for x, and we'll say x equals z sigma plus mu. For the first one, x equals negative 1.645 times the standard deviation plus the mean, and that gives us an SAT score of 325.2. And for the second one, we say 1.645 times the standard deviation plus the mean, and that gives us an SAT score of 706.8. So now we can say that the middle 90% of test takers scored between 325.2 and 706.8.